There is a question that has haunted every civilization, every philosopher, every child who has ever looked up at a dark sky. It is the oldest question, the deepest question, the one question that, no matter how advanced our instruments become, no matter how brilliant our theories grow, refuses to be fully answered. How did the universe begin? Not how did life begin, not how did Earth form, but how did everything, all of space, all of time, all of matter, all of energy, every atom in your body, every photon of starlight, every galaxy spinning in the void, how did all of it come into existence? And here is what makes this question so unsettling. The answer, as best as modern science can determine, is that approximately 13.8 billion years ago, everything we can observe was compressed into a region smaller than an atom, smaller than a proton, possibly smaller than anything we have a word for, and then it expanded, not into space, because space itself did not yet exist. It expanded as space. It became space. End quote. It became time. It became the laws of physics. It became the possibility of you sitting here, right now, listening to these words. That is not a metaphor. That is the current scientific consensus. And if it sounds impossible, if it sounds more like mythology than physics, then you are paying attention. Consider this. The observable universe stretches roughly 93 billion light-years from one edge to the other. It contains an estimated 2 trillion galaxies. Each galaxy holds between 100 billion and 1 trillion stars. The total number of stars in the observable universe is estimated at something like 700 sextillion. That is a 7 followed by 23 zeros. Every one of those stars, every planet orbiting them, every grain of dust drifting between them, every ray of light traveling through the dark, all of it traces back to a single event, a single moment, a single beginning that science calls the Big Bang. But even that name is misleading. There was no bang. There was no explosion in the way we understand explosions. There was no center, no edge, no outside into which things flew. What happened was stranger, more profound, and far more difficult to comprehend than any explosion could ever be. And here is what makes this story worth telling slowly, carefully, and completely. We actually have evidence. Not speculation, not faith, not philosophy alone. We have measurements. We have data. We have photographs, images captured by instruments, orbiting our planet that show us the universe as it looked just 380,000 years after the beginning. We can see the afterglow of creation itself, still washing over us from every direction. It is called the cosmic microwave background, and it is one of the most extraordinary things human beings have ever detected. It is a whisper from the birth of everything, still echoing across 13.8 billion years of cosmic time. And that whisper tells a story of unimaginable heat, staggering density, and a universe so different from the one we know today that it barely qualifies as the same place. By the end of tonight, you're going to understand what that whisper says. You are going to understand how scientists worked backwards from the present-day cosmos to reconstruct the first moments of existence. You are going to confront the limits of what physics can tell us and the terrifying boundary where our equations break down entirely. You are going to learn why the universe looks the way it does, why it is expanding, why it is cooling, and why, if you follow the story far enough, you arrive at a wall beyond which no theory, no instrument, and no human mind has ever been able to see. The first fraction of a second, the true origin, the point where everything began, and where everything we know about the laws of nature ceases to apply. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. What you are about to hear is not a story with a neat ending. It is a story that pushes against the very limits of human understanding. Every decade, we learn more. Every new telescope, every new satellite, every new particle accelerator peels back another layer. And yet the deepest layer, the layer that would tell us how and why the universe sprang into being, remains beyond our reach. We can get closer. We have gotten closer. We can now describe the state of the cosmos as it was just 1/1,000,000,000 of a trillionth of a trillionth of a second after the beginning. But the beginning itself, that first instant, that spark, that transition from nothing to everything, is still hidden behind a wall of physics that our theories cannot penetrate. And what we find when we press our faces against that wall is not an answer. It is something far more unsettling. It is the realization that the question may be deeper than any theory we have ever built. This is the story of the beginning, not a simplified version, not a summary. The full story, as far as science has been able to piece it together, with all its wonder, all its strangeness, and all the questions it still leaves unanswered. Now, let's begin. To understand the beginning, we first need to understand what we are looking at when we look up, because the universe is not just large. It is large on a scale that the human brain is simply not equipped to process. We evolved to navigate savannas, to judge the distance between trees, to estimate whether a predator was close enough to be dangerous. Our intuitions about size, speed, and time work beautifully for the world we inhabit. They fail completely when applied to the cosmos. So let us build our understanding step by step. Start with the Earth. It is a sphere roughly 12,742 kilometers in diameter. A large object by human standards, but a small one by planetary standards. Jupiter, the largest planet in our solar system, could fit approximately 1,300 Earths inside it. And Jupiter itself is tiny compared to the Sunday. The Sun contains 99.86% of all the mass in our solar system. If you were to hollow out the Sun, you could fit about 1.3 million Earths inside. The Sun is a yellow dwarf star, modest by stellar standards. The star Betelgeuse, in the constellation Orion, is so large that if you placed it where our Sun sits, its surface would extend past the orbit of Mars, possibly reaching as far as the orbit of Jupiter. Now here is the first comparison that begins to break your intuition. If the Sun were the size of a basketball, Earth would be a tiny grain of sand orbiting about 26 meters away. Jupiter would be roughly the size of a small marble, orbiting about 135 meters from that basketball-sized Sunday. And the nearest star, Proxima Centauri, would be another basketball sitting approximately 6,700 kilometers away. That is roughly the distance from New York to London. Two basketballs separated by an ocean. That is the scale of the gap between neighboring stars in our galaxy, and there are at least 100 billion stars in the Milky Way. Some estimates place the number closer to 400 billion. The Milky Way itself spans approximately 100,000 light-years from edge to edge. A light-year is the distance that light, the fastest thing in the universe, traveling at 299,792 kilometers per second covers in 1 year. That is about 9.5 trillion kilometers, so the Milky Way is roughly 950 quadrillion kilometers across. If you tried to drive across it at highway speed, say 100 kilometers per hour, it would take you approximately 1 trillion years. The universe is currently only 13.8 billion years old. You would need to multiply the entire age of the universe by roughly 72 just to make the drive across a single galaxy. And the Milky Way is just one galaxy among trillions. The nearest large galaxy, Andromeda, sits about 2.5 million light-years away. The observable universe, the sphere of space from which light has had time to reach us since the beginning, contains an estimated 2 trillion galaxies. 2 trillion. Each with billions or hundreds of billions of stars. The total number of stars is so vast that there are more stars in the observable universe than there are grains of sand on every beach on Earth. That comparison has been checked and rechecked by astronomers. It holds. There are roughly 7.5 times 10 to the 18th power grains of sand on Earth, and an estimated 7 times 10 to the 22nd power stars in the observable universe. The stars outnumber the sand grains by a factor of roughly 10,000. This is the arena in which our story takes place, not a galaxy, not a cluster of galaxies, the entire observable universe. And the claim of modern cosmology, supported by decades of evidence, is that all of it, every star, every galaxy, every photon, Every atom emerged from a state of almost unimaginable compression and heat, in an event that occurred 13.8 billion years ago. The story of how we came to understand this begins not with physicists, but with astronomers, and not with a grand theory, but with a simple observation. Consider how recently we understood our own place in the cosmos. For most of human history, people believed the Earth was the center of everything. The sun moved around us. The stars were lights fixed to a celestial sphere. The universe was small, comprehensible, and designed for our benefit. This picture began to crack in 1543, when Nicolaus Copernicus published his model placing the sun at the center. It fractured further when Galileo Galilei turned his telescope to the sky in 1610 and discovered the moons of Jupiter, proving that not everything revolved around the Earth. By the 18th century, astronomers understood that the sun was a star, one of many embedded in a vast disk of stars we call the Milky Way. But even then, the scale of the cosmos was drastically underestimated. As late as the early 20th century, many astronomers believed the Milky Way was the entire universe. There was nothing beyond it. The faint smudges of light visible through powerful telescopes, the so-called spiral nebulae, were thought to be gas clouds within our galaxy. It was not until 1924 that Edwin Hubble, using the 100-inch telescope at Mount Wilson in California, proved that the Andromeda Nebula was far outside the Milky Way. It was a separate galaxy, a separate island of billions of stars, sitting roughly 2.5 million light-years away. In a single observation, the known universe expanded by a factor of millions. What we thought was everything turned out to be one tiny neighborhood in a cosmos of unimaginable vastness. This pattern, the repeated demotion of humanity from the center to the periphery, from the special to the ordinary, is one of the defining themes of cosmology. We are not at the center of the solar system. We are not at the center of the galaxy. We are not at the center of the universe. There is, in fact, no center of the universe. Every point in space is equivalent to every other. The universe has no edge, no boundary, no preferred location. This is called the cosmological principle, and it is one of the foundational assumptions of modern cosmology. It says that, on the largest scales, the universe looks the same everywhere and in every direction, and observations confirm it. The cosmic microwave background is uniform to 1 part in 100,000. The distribution of galaxies, when averaged over scales of hundreds of millions of light-years, is smooth and homogeneous. The universe is, on the large scale, a remarkably uniform place. If you could somehow travel at the speed of light, the fastest speed permitted by the laws of physics, and set out from Earth right now, it would take you 4.2 years just to reach the nearest star. It would take you 100,000 years to cross our galaxy. It would take you 2.5 million years to reach Andromeda. And the most distant galaxies we can observe are over 13 billion light-years away. Even at the speed of light, you could never reach them, because the expansion of space is carrying them away faster than light can close the gap. There are galaxies we can see whose light left them billions of years ago, and which are now so far away, tens of billions of light-years, that no signal from us could ever reach them, and no signal from them could ever reach us again. They are beyond our cosmic horizon, forever inaccessible. We can see their past, frozen in ancient light, but we can never touch their present. In 1915, Albert Einstein published his general theory of relativity. It was a revolution in our understanding of gravity. Newton had described gravity as a force between objects. Einstein replaced this with something far more elegant and far more strange. He showed that gravity is not a force at all. It is the curvature of spacetime caused by mass and energy. A massive object like the sun bends the fabric of space around it, and planets follow curved paths through that warped geometry. This was confirmed in 1919, when the British astronomer Arthur Eddington measured the bending of starlight during a solar eclipse and found that the deflection matched Einstein's predictions exactly. But Einstein's equations had a consequence he did not expect. When applied to the universe as a whole, they predicted that space could not be static. It had to be either expanding or contracting. There was no stable middle ground. This troubled Einstein deeply. Like most scientists of his era, he believed the universe was eternal and unchanging. So he added a term to his equations, a cosmological constant specifically to hold the universe still. He later called this the biggest blunder of his career. Because the universe is not static, it is expanding. And the man who proved this was an American astronomer named Edwin Hubble. In 1929, working at the Mount Wilson Observatory in California, Hubble published a remarkable finding. He had been studying galaxies which at the time were still called nebulae, as many astronomers were not yet sure they were separate galaxies at all. By analyzing the light from these distant objects, Hubble noticed something extraordinary. The light was shifted toward the red end of the spectrum. This is called redshift, and it means the source of light is moving away from the observer. The further away a galaxy was, the greater its redshift. This meant that the further away a galaxy was, the faster it was moving away from us. This was not because the galaxies were flying through space like shrapnel from an explosion. It was because space itself was stretching. The galaxies were being carried apart by the expansion of the fabric of the universe. Imagine drawing dots on the surface of a balloon, then inflating that balloon. The dots do not move across the surface. The surface itself stretches, carrying the dots with it. And the further apart two dots are, the faster they appear to move away from each other, because there is more stretching surface between them. This is what Hubble discovered. The universe is like that balloon. Space is stretching, and everything in it is being carried along. Now here is the critical insight, the one that changed everything. If the universe is expanding today, then it was smaller yesterday, and smaller still the day before. If you run the clock backward, the universe contracts, galaxies come closer together, the space between them shrinks, the density increases, the temperature rises. If you keep rewinding, further and further, past the formation of galaxies, past the formation of stars, past the formation of atoms themselves, you eventually arrive at a state of infinite density and infinite temperature, compressed into a single point, a singularity. This is the Big Bang. Not an explosion in space, but the rapid expansion of space itself from an extraordinarily hot, extraordinarily dense initial state. The term Big Bang was actually coined in 1949 by the British astronomer Fred Hoyle, who used it mockingly. Hoyle favoured an alternative model called the steady state theory, which proposed that the universe had no beginning and no end, that new matter was continuously created to fill the gaps left by expansion. He called the rival theory the Big Bang as an insult. The name stuck, and Hoyle's steady state theory, despite its elegance, was eventually disproved by the evidence. That evidence came in 1964, and it arrived by accident. Two radio astronomers at Bell Telephone Laboratories in New Jersey, Arno Penzias and Robert Wilson, were working with a large horn-shaped antenna designed to detect radio signals bounced off satellite balloons. They encountered a persistent noise in their instrument, a faint microwave hum coming from every direction in the sky. They could not eliminate it. They checked the equipment. They cleaned pigeon droppings from the antenna. The noise remained. It was constant, uniform, and utterly mysterious. What Penzias and Wilson had stumbled upon was the cosmic microwave background radiation, or CMB. It is the afterglow of the Big Bang itself. When the universe was very young, about 380,000 years old, it had cooled enough for the first atoms to form. Before that moment, the universe was an opaque fog of charged particles and photons, all tangled together. When atoms formed, the photons were released. They streamed outward in every direction. Those photons have been traveling through space ever since, stretching with the expansion of the universe, cooling from a blazing inferno to a faint microwave glow. The temperature of this radiation today is approximately 2.725 Kelvin, just a few degrees above absolute zero. It fills all of space. It is everywhere, and it is the oldest light in the universe. Penzias and Wilson did not immediately understand what they had found, but physicists at nearby Princeton University Robert Dick, Jim Peebles, and others had predicted exactly such a signal. When they learned of the Bell Lab's discovery, they knew what it meant. The universe had a beginning. The Big Bang was real. Penzias and Wilson received the Nobel Prize in Physics in 1978, but the CMB was only the beginning of the evidence. Over the following decades, cosmologists developed an increasingly precise picture of the early universe, confirmed by observations from some of the most sophisticated instruments ever built. In 1989, NASA launched the Cosmic Background Explorer satellite, known as COBE. It measured the CMB with unprecedented precision and confirmed that it matches the spectrum of a perfect blackbody, an object that absorbs and emits all frequencies of radiation at a temperature of 2.725 Kelvin. It also detected tiny fluctuations in the temperature of the CMB, variations of about 1 part in 100,000. These fluctuations, these minuscule ripples in the afterglow of creation, are the seeds of all structure in the universe. They are the regions of slightly higher density that would eventually collapse under gravity to form galaxies, clusters of galaxies, and the vast cosmic web that spans the observable universe today. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, or WMAP, which mapped the CMB in far greater detail. And in 2009, the European Space Agency launched the Planck satellite, which achieved even higher resolution. The image produced by Planck, an oval map of the entire sky, colored in blues and reds and oranges, is one of the most important images in the history of science. It is a baby picture of the universe, taken when the cosmos was just 380,000 years old. And encoded in that image, in the sizes and patterns of the hot and cold spots, is an extraordinary amount of information. From the CMB, scientists have determined the age of the universe to within about 40 million years. They have determined that ordinary matter, the stuff that makes up stars, planets, and people, accounts for only about 5% of the total energy content of the universe. They have determined that roughly 27% is dark matter, a mysterious substance that does not emit or absorb light but exerts gravitational influence. And they have determined that approximately 68% is dark energy, an even more mysterious force that is driving the accelerating expansion of the universe. These are not rough guesses. These are measurements refined over decades by multiple independent instruments, and they all point to the same conclusion. The universe began in a hot, dense state approximately 13.8 billion years ago. It has been expanding and cooling ever since, and the faint microwave whisper that fills all of space is the direct observable remnant of that beginning. The discovery that dark energy makes up 68% of the universe was itself a shock that redrew our understanding of cosmic fate. In 1998, two independent teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, set out to measure the rate at which the expansion of the universe was slowing down. Gravity, they assumed, should be pulling everything back together, decelerating the expansion. They used Type Ia supernovae as distance markers. These stellar explosions have a known intrinsic brightness, so by measuring how dim they appear, astronomers can calculate how far away they are. What both teams found was the opposite of what they expected. The supernovae were dimmer than predicted. They were farther away than the decelerating models allowed. The expansion of the universe was not slowing down. It was speeding up. Some unknown force or property of space itself, was pushing the universe apart at an accelerating rate. This mysterious force was named dark energy, and its discovery earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. Dark energy is perhaps the deepest mystery in all of cosmology. It accounts for more than 2/3 of the total energy content of the universe, and we have almost no idea what it is. It may be a cosmological constant, the same term Einstein introduced and then rejected, a fixed energy density woven into the fabric of spacetime. Or it may be a dynamic field that changes over time, sometimes called quintessence. Or it may be something else entirely, something we have not yet imagined. What we do know is that dark energy is driving the universe apart faster and faster, and that its influence is growing as the universe expands. If dark energy persists, The long-term fate of the cosmos is a cold, dark, empty void, expanding forever, with every galaxy eventually fading beyond the horizon of every other. This is sometimes called the heat death of the universe. It is not a dramatic ending. It is a slow, silent fading, a whisper becoming silence. But here is where the story takes a darker turn, because knowing that the universe began is not the same as knowing how it began. The Big Bang model describes the evolution of the universe from a fraction of a second after the beginning onward. It describes how the universe expanded, how it cooled, how particles formed, how atoms came together, how stars ignited, how galaxies coalesced. It does all of this with extraordinary precision and extraordinary success, but it does not, and this is crucial, describe the beginning itself. It does not explain what caused the Big Bang. It does not explain what, if anything, came before. And it does not explain the very first instant, the moment of the singularity, because at that point, the mathematics of general relativity breaks down. The equations produce infinities. The temperature becomes infinite. The density becomes infinite. Spacetime curves so tightly that it ceases to have meaning. The theory collapses, and we are left staring at a wall. To grasp just how far back we must travel, consider a scale comparison. If the entire history of the universe, all 13.8 billion years, were compressed into a single calendar year, with the Big Bang occurring at midnight on January 1st, then our solar system would not form until September. Life on Earth would not appear until October. Dinosaurs would roam the planet during the last week of December. The entire recorded history of human civilization, writing, agriculture, cities, empires, wars, science, would occupy the final 14 seconds before midnight on December 31st. 14 seconds. That is us. That is everything we have ever known. And the event we are trying to understand, the beginning, is the stroke of midnight on January 1st, the moment the clock started. Now try to imagine something even more extreme. The Big Bang model describes the universe back to approximately 1 Planck time after the beginning. A Planck time is the smallest meaningful unit of time in physics. It is approximately 5.4 times 10 to the negative 44 seconds. That is a decimal point followed by 43 zeros, and then a 5. It is unimaginably brief. The amount of time it takes light to cross the diameter of a proton is already beyond comprehension, and a Planck time is trillions of times shorter than even that. Yet everything before that instant, the true moment of origin, is hidden behind a curtain that our current physics cannot penetrate. If you were to place the entire observable universe on one end of a scale and a single hydrogen atom on the other, the ratio of their sizes would be approximately 10 to the power of 36. That is a 1 followed by 36 zeros. That number is enormous. But the ratio between the size of the observable universe and the Planck length, the smallest meaningful distance in physics, is 10 to the power of 61. The universe of the very small is, in a sense, even more vast and strange than the universe of the very large. And it is in that realm, the realm of the unimaginably tiny, that the secret of the beginning is hidden. What happened at the very beginning? What happened in the first fraction of a second? What caused the universe to come into existence at all? These are not merely difficult questions. They may be the most profound questions the human mind has ever asked. And what scientists found when they tried to answer them was not clarity, but deeper and more bewildering mystery. The problem is not that we have no theory of the beginning. The problem is that we have an extraordinarily successful theory that works brilliantly up to a point, and then, at the most critical moment, falls apart entirely. The standard Big Bang model, combined with the physics of the very small quantum mechanics, gives us a detailed narrative of the universe's evolution starting from a tiny fraction of a second after the beginning. In the first few microseconds, quarks and gluons existed in a superheated soup called a quark-gluon plasma. As the universe expanded and cooled, quarks combined to form protons and neutrons. Within the first 3 minutes, yes, 3 minutes, the process of Big Bang nucleosynthesis produced the first atomic nuclei, mostly hydrogen, about 25% helium by mass, and trace amounts of lithium and deuterium. These proportions have been measured with great precision, and they match the predictions of the Big Bang model to remarkable accuracy. For 380,000 years, the universe remained a hot, dense plasma. Photons could not travel freely because they were constantly scattered by free electrons. The universe was opaque. Then, as temperatures dropped to about 3000 Kelvin, electrons combined with nuclei to form neutral atoms. This is called recombination. The photons were released. The universe became transparent. And those freed photons are what we now detect as the cosmic microwave background. The CMB is not just evidence of the Big Bang. It is a snapshot of the universe at age 380,000 years, frozen in light and preserved across billions of years of cosmic expansion. After recombination, the universe entered what cosmologists call the Dark Ages. No stars had yet formed. The cosmos was filled with clouds of neutral, hydrogen, and helium, drifting in near total darkness. Gravity slowly pulled matter into denser clumps. Over hundreds of millions of years, these clumps grew massive enough to collapse under their own weight, igniting nuclear fusion. The first stars were born. They were enormous, perhaps 100 to 1,000 times the mass of our Sun, and they burned hot and fast, flooding the universe with ultraviolet light that reionized the surrounding hydrogen. The Dark Ages ended. The cosmic dawn had arrived. The first galaxies assembled over the next few billion years. Smaller protogalaxies merged to form larger ones. Supermassive black holes formed at their centers. Stars lived, died, exploded as supernovae, seeding the cosmos with heavier elements, carbon, oxygen, iron, gold, forged in their cores and scattered across space. New generations of stars formed from these enriched clouds, and around them, planets condensed. Chemistry grew more complex. On at least one small rocky world orbiting an ordinary star in an ordinary galaxy, that chemistry became biology. And here we are. This narrative is not speculation. Each step is supported by multiple lines of evidence. The abundances of light elements confirm nucleosynthesis. The CMB confirms recombination. The Hubble Space Telescope, and more recently the James Webb Space Telescope, launched in 2021, have imaged galaxies from just a few 100 million years after the Big Bang. The story holds together. It is one of the great triumphs of modern science. But let us slow down and examine this timeline more carefully, because the details of the early universe are not merely interesting, they are essential to understanding where the story fails. In the first 10 to the negative 43 seconds, 1 Planck time, we have no theory that applies. This is the unknown zone, the blank page at the start of cosmic history. We will return to it later. From 1 Planck time to approximately 10 to the negative 36 seconds, the universe is thought to have been in the grand unification epoch. During this phase, 3 of the 4 fundamental forces of nature, the strong nuclear force, the weak nuclear force, and the electromagnetic force were unified into a single force. Only gravity was separate. The temperatures during this epoch were unimaginable, on the order of 10 to the 28th Kelvin or higher. No particle accelerator ever built comes close to probing these energies. The Large Hadron Collider at CERN, the most powerful machine ever constructed by human beings, reaches energies of about 13 tera-electron-volts. The grand unification energy is roughly 1 trillion times higher. We are extrapolating our physics far beyond anything we can test in a laboratory, and we are trusting our extrapolations to hold. This is a significant assumption. It may not be warranted. At about 10 to the negative 36 seconds, the grand unified force is thought to have split apart, with the strong force separating from the electroweak force. This symmetry breaking may have been the trigger for cosmic inflation, the exponential expansion we will discuss shortly. The details depend on the specific model of grand unification, and there are many competing models, none of which has been definitively confirmed. At approximately 10 to the negative 12 seconds, 1 picosecond after the beginning, the electroweak symmetry broke. The electromagnetic force and the weak nuclear force, which had been unified as the electroweak force, separated into the 2 distinct forces we observe today. The Higgs field, discovered at CERN in 2012 through the detection of the Higgs boson, acquired its non-zero value during this transition. This is the mechanism that gives mass to fundamental particles. Without the Higgs field, electrons would be massless, atoms could not form, and the universe as we know it could not exist. The discovery of the Higgs boson was one of the great triumphs of the early 21st century, and it confirmed that the electroweak theory, developed by Sheldon Glashow, Abdus Salam, and Steven Weinberg in the 1960s and 70s, is correct. At approximately 10 to the negative 6 seconds, 1 microsecond, the quark-gluon plasma condensed. Quarks, which had been free to roam the hot, dense soup of the early universe, became confined inside protons and neutrons. This transition is called quark confinement, and it is a consequence of the strong nuclear force growing stronger at low energies. Before this moment, the universe was a sea of free quarks and gluons, a state of matter that has been briefly recreated in heavy ion collisions at the relativistic heavy ion collider in Brookhaven, New York, and at the Large Hadron Collider. These experiments have confirmed that the quark-gluon plasma is real, that it behaves as predicted, and that the early universe was indeed a quark soup in its first microsecond. At about 1 second, the temperature had dropped to roughly 10 billion Kelvin. Neutrinos, ghostly particles that barely interact with matter, decoupled from the rest of the universe. They stopped interacting and began streaming freely through space. These primordial neutrinos should still exist today, forming a cosmic neutrino background analogous to the cosmic microwave background. Their temperature is predicted to be about 1.95 Kelvin, even colder than the CMB. We have not yet directly detected them. They are extraordinarily difficult to detect because they interact so weakly, but their existence is predicted with high confidence, and their effects on the expansion rate of the universe and the formation of structure have been indirectly measured. Also, at about 1 second, the balance between protons and neutrons was frozen. In the first second, protons and neutrons were constantly converting back and forth through interactions mediated by the weak force. As the universe cooled, these reactions slowed and eventually stopped, locking in a ratio of approximately 7 protons for every 1 neutron. This ratio is crucial because it determines the final abundances of light elements. If the ratio had been different, if the freezing had happened earlier or later, or if the strength of the weak force had been slightly different, the primordial abundances of hydrogen, helium, and lithium would have been different, and the chemical history of the universe would have unfolded in a completely different way. Between about 10 seconds and 20 minutes after the Big Bang, nucleosynthesis occurred. Protons and neutrons fused to form the first atomic nuclei. The vast majority of the protons remained as individual hydrogen nuclei. About 25% of the mass ended up in helium-4 nuclei, each containing 2 protons and 2 neutrons. Tiny amounts of deuterium, helium-3, and lithium-7 were also produced, and then nucleosynthesis stopped. The universe had expanded and cooled below the temperatures needed for nuclear fusion. No elements heavier than lithium were produced. Everything heavier, carbon, nitrogen, oxygen, silicon, iron, gold, uranium, would have to wait for the first stars, hundreds of millions of years later. The precision with which Big Bang nucleosynthesis predicts the observed abundances of light elements is one of the strongest pieces of evidence for the Big Bang model. The predicted and observed ratios of hydrogen, helium, and deuterium agree to within a few percent. This agreement is not trivial. It depends on the density of ordinary matter in the early universe, the number of neutrino species, the strength of nuclear forces, and the expansion rate. Getting all of these right simultaneously is a powerful test, and the Big Bang model passes it convincingly. Then came the long wait. For 380,000 years, the universe was a plasma, a hot, dense fog, in which photons were trapped, constantly bouncing between free electrons. This era is sometimes called the Cosmic Dark Age, before the real Dark Ages, because although the universe was filled with light, that light could not travel in a straight line. It was scattered in every direction, like headlights in thick fog. The universe was brilliant but opaque. Then, at a temperature of roughly 3000 Kelvin, something extraordinary happened. The universe cooled enough for electrons to be captured by atomic nuclei, forming neutral atoms. This process, somewhat misleadingly called recombination misleading, because the electrons and nuclei were combining for the first time, not recombining, changed the universe forever. The fog cleared. Photons were free to travel in straight lines for the first time. The universe became transparent, and the light released at that moment, the cosmic microwave background, has been traveling through space ever since, stretching and cooling with the expansion of the universe, until it reaches our instruments today as a faint microwave glow at 2.725 Kelvin. The CMB is not just a piece of evidence, it is the Rosetta Stone of cosmology. Everything we know about the shape, age, composition, and history of the universe is encoded in its patterns. And the fact that it exists, that we can detect it, measure it, and decode it is perhaps the most fortunate accident in the history of science. But here's the problem. Go back further, earlier than nucleosynthesis, earlier than the quark-gluon plasma, earlier than the first microsecond. Approach the singularity. What happens? The temperature rises. At 1 second after the Big Bang, the temperature of the universe was approximately 10 billion Kelvin. At 1 microsecond, it was about 10 trillion Kelvin. At 1 picosecond, 1 trillionth of a second, temperatures were roughly 10 to the 15th Kelvin. As you approach the Planck time, 5.4 times 10 to the negative 44 seconds, the temperature reaches the Planck temperature, approximately 1.4 times 10 to the 32 Kelvin. Numbers so large they have no analogue in human experience. No physical process we have ever observed approaches these temperatures. No laboratory on Earth can even come close. And at the Planck scale, something fundamental happens. The two great pillars of modern physics, general relativity, which describes gravity and the large-scale structure of spacetime, and quantum mechanics, which describes the behavior of particles at the smallest scales, come into direct conflict. General relativity treats spacetime as smooth and continuous. Quantum mechanics says that at small enough scales, everything is fuzzy, probabilistic, and uncertain. At the Planck scale, where distances are about 1.6 times 10 to the negative 35 meters, and times are about 5.4 times 10 to the negative 44 seconds, both theories must be applied simultaneously. And they cannot be. Their mathematics is incompatible. The predictions they make contradict each other. The equations break down. We get nonsensical answers, infinities, paradoxes, meaninglessness. This is the crisis at the heart of cosmology. We need a theory of quantum gravity, a single framework that unites general relativity and quantum mechanics to understand the very first instant of the universe. And we do not have one. Despite decades of effort by some of the most brilliant physicists who have ever lived, no complete, experimentally verified theory of quantum gravity exists. String theory, loop quantum gravity, causal set theory, these are candidates, but none has been confirmed by observation. The beginning of the universe is locked behind a door for which we do not yet possess the key. And it gets worse. Even setting aside the quantum gravity problem, the standard Big Bang model has serious issues that became apparent as early as the 1970s. These are not minor problems. They are fundamental puzzles that suggest something critical is missing from our understanding. The first is called the horizon problem. Look at the CMB. It is astonishingly uniform. The temperature is the same in every direction to within 1 part in 100,000. This means that regions of the universe that are now tens of billions of light-years apart had, at the time the CMB was emitted, almost exactly the same temperature. But here is the difficulty. According to the standard Big Bang model, those regions were never in causal contact. Light had not had enough time to travel between them. They could not have exchanged heat. They could not have communicated in any way. So how did they end up at the same temperature? It is as if you opened 2 ovens in different countries and found them set to exactly the same temperature, down to 100,000th of a degree, despite no one having coordinated them. Something is wrong with our assumptions. The second problem is called the flatness problem. General relativity allows spacetime to have different geometric shapes. It can be positively curved, like the surface of a sphere. It can be negatively curved, like a saddle, or it can be flat, like a tabletop. The geometry depends on the total energy density of the universe. Observations show that the universe is flat, or very nearly flat, to extraordinary precision. The density parameter, called omega, is measured to be very close to 1. But the equations of the Big Bang model say that any deviation from perfect flatness at the beginning would have grown rapidly over time. If omega had been even slightly greater than 1 in the first moments, the universe would have collapsed back on itself long ago. If it had been even slightly less than 1, the universe would have expanded so fast that galaxies could never have formed. The fact that omega is still so close to 1 today, after 13.8 billion years of expansion, means that at the very beginning, it must have been fine-tuned to an almost absurd degree. To something like 1 part in 10 to the 60, that is a 1 followed by 60 zeros of precision. There is no mechanism in the standard Big Bang model to explain why the initial conditions were so precisely calibrated. The third problem is the magnetic monopole problem, or more broadly, the problem of exotic relics. Many theories of particle physics predict that the extreme temperatures of the very early universe should have produced vast quantities of massive, stable particles, magnetic monopoles, domain walls, cosmic strings. These should be everywhere, but we observe none. Where did they go? A magnetic monopole is a hypothetical particle that carries a single magnetic charge, a north pole without a south pole, or vice versa. In ordinary experience, magnets always have 2 poles. Cut a bar magnet in half, and you get 2 smaller magnets, each with its own north and south pole. You can never isolate a single pole. But grand unified theories predict that magnetic monopoles should have been produced in enormous quantities during the symmetry-breaking transitions of the very early universe. Their predicted mass is enormous, roughly 10 to the 16th times the mass of a proton, or about 100,000th of a milligram. That may sound small, but for a subatomic particle, it is colossal, and the predicted abundance is high. There should be approximately as many monopoles as protons in the universe. Every detector, every experiment, every observation should be swimming in them. But no magnetic monopole has ever been detected. Despite decades of searching, despite experiments at particle accelerators and in cosmic ray detectors, and even in ocean floor sediments, not a single monopole has been found. This is not a minor embarrassment. It is a profound failure of prediction, and it was one of the main motivations for the theory of inflation. These 3 problems, the horizon problem, the flatness problem, and the monopole problem, are not minor blemishes on an otherwise perfect theory. They are glaring, fundamental inconsistencies that demand explanation, and the answer that most cosmologists have converged upon is both brilliant and deeply strange. It is called cosmic inflation. In 1979, a young physicist at Stanford, named Alan Guth, was thinking about the monopole problem. He was trying to understand why the universe appeared to be free of the exotic particles that grand unified theories predicted should exist, and he stumbled upon an idea that would transform cosmology. Guth proposed that in the very first moments after the Big Bang, specifically between approximately 10 to the negative 36 seconds and 10 to the negative 32 seconds, the universe underwent a period of exponential expansion. Not the slow, steady expansion that Hubble discovered, an explosion of expansion so violent, so rapid, that the universe doubled in size roughly every 10 to the negative 37 seconds. In that tiny sliver of time, the universe grew by a factor of at least 10 to the 26. Some models suggest it grew by a factor of 10 to the 50 or more. That is a number so large that comparison becomes meaningless. Here is a scaled comparison to try to convey the magnitude. Imagine a single proton. Its diameter is roughly 10 to the negative 15 meters. After inflation, that proton-sized region of space would have expanded to something larger than the entire observable universe today. The observable universe, 93 billion light-years across, could have begun as something smaller than a subatomic particle. Let that sink in. Inflation solves all 3 problems at once, and it does so elegantly. The horizon problem disappears because regions that appear to be disconnected today were, before inflation, close enough to be in thermal contact. They had time to reach the same temperature. Then inflation stretched them apart so fast that they now appear to have been forever separated. The flatness problem disappears because inflation stretches spacetime so dramatically that any initial curvature is smoothed out, just as the surface of a balloon appears flat if you inflate it to an enormous size. The monopole problem disappears because any exotic particles produced before inflation were diluted to negligible density by the tremendous expansion. Inflation also explained something that the standard Big Bang model had simply assumed: the origin of the tiny fluctuations in the CMB. Before inflation, quantum fluctuations, the random, inherent jitteriness of the quantum vacuum, existed at the subatomic scale. Inflation took these microscopic fluctuations and stretched them to cosmological sizes. These stretched quantum fluctuations became the seeds of all structure in the universe. Every galaxy, every cluster, every void in the cosmic web can be traced back to a quantum fluctuation from the inflationary epoch, amplified to cosmic proportions. This is worth pausing on. The largest structures in the universe, galaxy clusters, spanning hundreds of millions of light-years, began as quantum fluctuations smaller than an atom. The microscopic randomness of the quantum world was inflated into the architecture of the cosmos. The very small became the very large. And we can see the imprint of this process in the CMB, in the precise pattern of hot and cold spots mapped by Planck and WMAP. Think of it this way. If you could zoom in on a tiny patch of the CMB, a region that corresponds to a volume of space much smaller than a proton before inflation, you would find the fingerprint of a quantum event from 13.8 billion years ago. That quantum event, amplified by inflation, became a region of slightly higher density. That region attracted more matter through gravity. Over hundreds of millions of years it grew into a galaxy. That galaxy formed stars. Those stars produced heavy elements. Those elements formed planets. And on one of those planets, beings evolved who are now mapping the CMB and tracing their origins back to that quantum fluctuation. The chain of causation stretches from the Planck scale to the cosmic scale, from the smallest conceivable fluctuation to the largest structures in existence, and every link in that chain is governed by known physics. Every link has been tested and confirmed. But here is where we must be honest about what we do not know. The theory of inflation, while powerful, is not a single theory. It is a framework, a class of models that share the feature of exponential expansion but differ in their details. The original model proposed by Guth had a problem, known as the graceful exit problem. Inflation, once started, did not stop cleanly enough to produce a uniform universe. This was solved in the early 1980s by André Linde, who proposed chaotic inflation, and independently by Andreas Albrecht and Paul Steinhardt, who proposed new inflation. Since then, hundreds of inflationary models have been proposed. They differ in the shape of the inflaton potential, the mathematical function that describes how the energy of the inflaton field changes over time. Each model makes slightly different predictions about the CMB. The problem is that many of these models fit the data. The CMB observations are precise enough to rule out some models, but not precise enough to single out one. We know that inflation, or something very like it, occurred. We do not know which version of inflation is correct. And some physicists have argued that the landscape of possible inflationary models is so vast that inflation can accommodate almost any observation, making it difficult to falsify. This is a serious criticism. A theory that can explain anything predicts nothing. One key prediction of inflation that has not yet been confirmed is the existence of primordial gravitational waves. Inflation should have produced ripples in spacetime gravitational waves at the same time it produced the density fluctuations that seeded galaxy formation. These gravitational waves would leave a distinctive imprint on the polarization of the CMB, a pattern called B-mode polarization. In 2014, the BICEP-2 experiment announced the detection of B-mode polarization, which was initially hailed as the first direct evidence of inflation. But subsequent analysis, incorporating data from the Planck satellite, showed that the signal was likely caused by dust in our own galaxy, not by primordial gravitational waves. The detection was retracted. The search continues. Future experiments, including BICEP array, the Simons Observatory, and the proposed Lightbird satellite, may eventually detect the primordial gravitational wave signal. If they do, it would be one of the most important discoveries in the history of cosmology, providing direct evidence that inflation occurred and constraining the energy scale at which it happened. The evidence for inflation is strong, though not yet definitive. The predictions it makes about the CMB, the statistical properties of the temperature fluctuations, the spectrum of perturbations, the near-scale invariance of the power spectrum match the observations remarkably well. Inflation is not proven in the same way that the expansion of the universe is proven, but it is the leading theoretical framework for understanding the earliest moments of cosmic history, and no serious competitor has achieved the same level of explanatory success. But even inflation does not solve the ultimate problem. Inflation explains what happened after 10 to the negative 36 seconds. It does not explain what happened before. Number 5. It does not explain what caused inflation to begin. It does not explain the singularity. It does not explain how or why the universe came into existence at all. These questions remain open, and they push us to the very edge of what science can currently address. But here's what makes this truly terrifying. The deeper we dig, the more we find that the foundations of our understanding are not as solid as they appear. The Big Bang model works. Inflation works. But they work in the way a map works, accurately describing the terrain while revealing nothing about who drew the map or why the terrain exists at all. So what did come before the Big Bang? What lies on the other side of the Planck wall? Scientists have not been idle in the face of these questions. For decades, some of the most creative minds in theoretical physics have proposed answers. Each attempt is bold, each attempt is imaginative, and each attempt, in its own way, reveals just how far we still are from the truth. Let us examine the most significant proposals one by one. The first is the Hartle-Hawking no-boundary proposal. In 1983, the physicists James Hartle and Stephen Hawking published a paper that attempted something radical. They tried to eliminate the singularity altogether. Their idea was rooted in quantum mechanics, specifically in the path integral formulation developed by Richard Feynman. In this approach, instead of asking what happened at the beginning, you ask, what is the probability that the universe has a particular configuration? You sum over all possible histories, all possible paths through time, and calculate the most likely outcome. Hartle and Hawking proposed that if you treat time near the Big Bang not as ordinary time but as a dimension similar to space using a mathematical technique called Wick rotation, where time becomes imaginary time in the mathematical sense, then the singularity disappears. Instead of a sharp point at the beginning, you get a smooth, rounded geometry, like the bottom of a bowl or the south pole of the Earth. There is no edge, there is no boundary. The universe simply is. It has a finite past, but no beginning in the traditional sense. Just as you can walk south on the Earth's surface until you reach the South Pole, but there is no point south of the South Pole, you can trace the universe back in time, but there is no moment before the beginning. The question, what happened before the Big Bang, becomes meaningless, like asking, what is north of the North Pole? It is a beautiful idea. Hawking himself considered it his most important contribution to physics, but it has significant limitations. The no-boundary proposal relies on a formulation of quantum gravity that we do not yet fully understand. The calculations are extraordinarily difficult, and different approaches to performing them yield different results. Some physicists have argued that the no-boundary proposal, when calculated correctly, predicts a universe that looks nothing like ours, an empty, featureless cosmos rather than the rich, structured one we observe. Others have defended it, proposing modifications and refinements. The debate continues. The no-boundary proposal remains a possibility, but it has not been confirmed by any observation, and its mathematical foundations are contested. There is a deeper issue with the no-boundary proposal that deserves attention. Even if the mathematics works, the interpretation is profoundly strange. What does it mean to say that time becomes imaginary near the beginning? Imaginary time is a mathematical concept. It involves multiplying ordinary time by the square root of -1. It is a tool, a trick of the calculus, that makes certain equations easier to solve. But does it correspond to physical reality? Does time really change its character near the Big Bang, becoming spatial? Or is this just a mathematical convenience that tells us nothing about what actually happened? Hawking argued that the distinction between mathematical formalism and physical reality is meaningless in quantum mechanics, that the equations are the reality. But not all physicists agree. And the question of what imaginary time means in a physical sense remains deeply controversial. There is also the question of uniqueness. The no-boundary proposal does not predict that our universe is the only possible outcome. It assigns probabilities to different configurations. Our universe, with its particular physical constants and initial conditions, is the most probable outcome according to some versions of the calculation, but not according to others. If the most probable outcome is an empty universe, as some calculations suggest, then the no-boundary proposal fails to explain why our universe is not empty. It would need to be supplemented by some other principle or mechanism, and we do not know what that would be. The second major attempt to understand the beginning is the theory of eternal inflation, which grows naturally out of the inflationary model described earlier. In the standard picture, inflation begins, the universe expands exponentially, and then inflation ends. The energy stored in the inflation-driving field, called the inflaton, is released, reheating the universe and producing the hot, dense plasma from which everything we see subsequently emerged. But in the early 1980s, physicists including Andrei Linde and Alexander Vilenkin realized that inflation might not end everywhere at once. In some regions, the inflaton field might decay and inflation might stop, creating a pocket universe, a region where the Big Bang plays out and galaxies form. But in other regions, inflation might continue, driving further exponential expansion. And within those inflating regions, new pocket universes might form, each with its own Big Bang, each potentially with different physical constants, different particle masses, even different dimensions of space. In this picture, the Big Bang that produced our observable universe was not the beginning of everything. It was a local event, a bubble that formed within a much larger, eternally inflating multiverse. There may be an infinite number of such bubbles, each containing its own universe, each separated by inflating space that expands too fast for any signal to ever cross. We can never see them. We can never contact them. We can never test for them directly, but the theory predicts that they exist. The numbers are striking. If eternal inflation is correct, the multiverse could contain a virtually infinite number of pocket universes. The total amount of space could be growing exponentially, faster than the speed of light, at every instant. Our observable universe, all 93 billion light-years of it, with its 2 trillion galaxies and 700 sextillion stars, would be an infinitesimal bubble in an incomprehensibly vast foam of universes. Eternal inflation solves the question of what caused the Big Bang by embedding it in a larger process that may have no beginning and no end. Inflation itself is the fundamental state. Individual Big Bangs are merely local fluctuations within an eternally inflating background. But this raises an immediate objection. If the multiverse is infinite and cannot be observed, is it science? Can a theory that makes no testable predictions about the other universes really be called scientific? This is a matter of fierce debate among physicists and philosophers. Some, like Linde, argue that eternal inflation is a natural consequence of well-established inflationary physics and should be taken seriously. Others, like Paul Steinhardt, who, ironically, helped develop the inflationary model in the first place, argue that a theory which can explain anything explains nothing, and that the multiverse is a sign that something has gone wrong with the approach. There is another difficulty. In an eternally inflating multiverse, everything that can happen does happen, somewhere. Every possible arrangement of matter and energy is realized in some pocket universe. Every possible history plays out. Every possible version of you exists somewhere in the infinite foam. This sounds liberating, but it is actually a scientific nightmare. Because if everything happens, then nothing is surprising. No observation can ever rule the theory out. because any observation is consistent with some version of the multiverse. This is called the measure problem, and it is one of the deepest unsolved challenges in inflationary cosmology. How do you assign probabilities in an infinite universe? How do you predict anything at all when everything is possible? Physicists have proposed various solutions to the measure problem: cutoff measures, volume weighting, causal diamond measures, but none has achieved consensus. The problem remains open, and it casts a shadow over the entire multiverse concept. And yet, eternal inflation has a compelling feature that is hard to dismiss. It may not have had a beginning. In 2003, the physicists Arvind Borde, Alan Guth, and Alexander Vilenkin proved a theorem now known as the BGV theorem, which states that any universe that has been, on average, expanding throughout its history must have had a beginning. This seems to rule out an eternally past expanding universe, but the theorem has loopholes. The theorem, it applies to universes that are, on average, expanding. It does not apply to universes that are contracting, or to universes that are not expanding on average, or to static universes. Some versions of eternal inflation may evade the theorem. The question of whether the multiverse itself had a beginning remains unresolved. The third attempt is the cyclic model, and it represents a dramatic departure from the inflationary paradigm. The cyclic model, developed primarily by Paul Steinhardt and Neil Turok in the early 2000s, proposes that the Big Bang was not the beginning of the universe but merely the latest in a potentially infinite series of cosmic cycles. In this picture, our universe exists on a three-dimensional membrane, a brane, floating in a higher dimensional space. Another brane exists parallel to ours, separated by a small extra dimension. The two branes are attracted to each other. They collide. The energy of the collision produces a Big Bang. The universe expands, cools, and eventually, driven by dark energy, the expansion dilutes all matter and radiation to near nothingness. The branes are drawn together again. They collide again. Another Big Bang occurs. Another cycle begins. In this model, there is no singularity in the traditional sense. The collision between branes is violent but finite. Temperatures and densities are extremely high, but do not reach infinity. There is no need for inflation because the problems inflation was designed to solve, the horizon problem, the flatness problem, are resolved by the long, slow evolution of the universe during the contraction phase of the previous cycle. The universe had plenty of time, in the previous cycle, for distant regions to come into thermal equilibrium. The flatness was established over eons, not in a tiny fraction of a second. The cyclic model is elegant and avoids many of the conceptual difficulties of inflation, but it has its own challenges. It requires the existence of extra dimensions, as predicted by string theory, which has not been experimentally confirmed. It requires a specific mechanism for the brane collision that is not yet fully understood. And it makes predictions about the CMB that are subtly different from those of inflation in particular. It predicts a different pattern of gravitational waves from the early universe. Future observations, particularly from gravitational wave detectors, may be able to distinguish between the two models, but for now, the cyclic model remains a viable but unconfirmed alternative. The cyclic model also raises profound questions about time and memory. If the universe undergoes an infinite number of cycles, does any information survive from one cycle to the next? The answer, in most versions of the model, is no. Each cycle begins with a clean slate. The expansion and dilution phase erases all traces of the previous cycle. Black holes evaporate, particles decay, structures dissolve. By the time the next collision occurs, the universe has been smoothed and emptied to the point where nothing of the previous cycle remains. Each Big Bang is a fresh start. Each universe begins in ignorance of its predecessors. If this is true, then the question of how many cycles have occurred is not only unanswerable, but meaningless. There is no observable difference between a universe that has cycled once and a universe that has cycled 1 trillion times. The past, beyond the last Big Bang, is erased. There is something both comforting and disturbing about this idea. Comforting because it means the universe is eternal, it has no beginning and no end, just an endless rhythm of creation and destruction. Disturbing because it means that nothing is permanent. Every civilization, every thought, every achievement is eventually wiped clean. The slate is reset. The story starts over. And no one in the next cycle will ever know that we existed. Consider a simple analogy. If you write a message on a chalkboard, erase it, and write a new message, the chalkboard does not remember the old message. It is gone, completely and irretrievably gone. The cyclic universe is the cosmic chalkboard. Each cycle writes a new story, and each story is erased before the next begins. The fourth attempt comes from loop quantum gravity, one of the major approaches to quantum gravity that competes with string theory. In loop quantum gravity, or LQG, space-time is not a smooth, continuous fabric. It is made up of discrete units, tiny loops, or networks, woven together at the Planck scale. Space has a granular structure, like a fabric made of incredibly fine threads. Time proceeds in discrete ticks, each one Planck time in duration. This granularity has a profound consequence for cosmology. When physicists apply the principles of LQG to the early universe, a field called loop quantum cosmology, they find that the singularity disappears. The universe does not collapse to a point of infinite density. Instead, as the density approaches the Planck density, roughly 5 times 10 to the 96 kilograms per cubic meter, quantum gravitational effects generate a repulsive force that halts the contraction and triggers a bounce. The universe rebounds. Expansion replaces contraction. The Big Bang becomes a big bounce. In this picture, our universe existed before the Big Bang. It was a collapsing universe, contracting under gravity, growing hotter and denser. When it reached the Planck density, it bounced, and what we call the Big Bang was actually the moment of that bounce. Time does not begin at the Big Bang. It extends backward, through the bounce, into a previous epoch of cosmic history. There may have been a universe before ours, contracting for billions of years, whose collapse and rebound gave birth to the expanding universe we inhabit today. Loop quantum cosmology is mathematically rigorous and avoids the singularity in a natural, principled way. But like the cyclic model, it requires a theoretical framework loop quantum gravity that has not been experimentally confirmed. And the details of the bounce, the nature of the preceding universe, and the question of whether the bounce has happened more than once remain open and actively debated. The key insight of loop quantum cosmology is that there is a maximum density in nature, the Planck density. Just as there is a maximum speed, the speed of light, there is a maximum amount of matter and energy that can be packed into a given volume of space. When that limit is reached, quantum gravity effects create an effective repulsive force that pushes outward, preventing the formation of a singularity. This is analogous to what happens in quantum mechanics with atoms. Classical physics predicts that electrons should spiral into the nucleus, emitting radiation as they go. They should crash into the center. Quantum mechanics prevents this by establishing a minimum orbital radius, the ground state. In the same way, loop quantum gravity prevents the universe from collapsing to a point. There is a ground state for the universe itself, a minimum volume below which spacetime cannot be compressed. This is a conceptually revolutionary idea. It suggests that the Big Bang was not the beginning of time, but a transition, a violent, cataclysmic transition, but a transition nonetheless between a previous collapsing phase and our current expanding phase. The question then becomes, what was the universe like before the bounce? Was it similar to our universe, with galaxies and stars and planets? Or was it fundamentally different? Loop quantum cosmology offers some tentative answers. Calculations suggest that the bounce is symmetric. The universe before the bounce was a mirror image of the universe after, contracting where ours is expanding, cooling where ours was heating. But the details are sensitive to the model, and different versions of loop quantum cosmology give different answers. One of the most exciting aspects of the big bounce scenario is that it might be testable. If the bounce left an imprint on the universe, a characteristic pattern in the CMB, for instance, or a distinctive spectrum of gravitational waves, then future observations could potentially detect it. Several research groups are working on identifying the observational signatures of loop quantum cosmology, and the next generation of CMB experiments and gravitational wave observatories may provide crucial data. This is cosmology at its best, bold theoretical ideas that make specific, falsifiable predictions which can be tested against the real universe. The fifth attempt, and perhaps the most philosophically radical, comes from the idea that the universe might have arisen from nothing at all. In 1973, Edward Tryon, a physicist at Columbia University, proposed that the universe might be a quantum fluctuation of the vacuum. In quantum mechanics, even empty space, the vacuum is not truly empty. It seethes with virtual particles that pop into and out of existence, borrowing energy for brief instants. Tryon suggested that the entire universe could be such a fluctuation, a bubble of spacetime and energy that emerged from a quantum vacuum and, through inflation, grew to the scale we observe today. The total energy of the universe might be exactly zero, the positive energy of matter and radiation precisely balanced by the negative energy of gravity, making the universe a free lunch, as Tryon put it, that required no energy to create. This idea was developed further by Alexander Vilenkin in the 1980s. Vilenkin proposed that the universe could tunnel into existence from literally nothing, not from a pre-existing vacuum, not from a quantum field, but from a state of absolute nothingness. Using the mathematics of quantum tunneling, he showed that there is a non-zero probability for a small, closed universe to appear spontaneously out of nothing, and that once it appeared, inflation would take over and expand it to cosmological scales. The universe, in this view, is the ultimate free lunch. It came from nothing, it required nothing, and its total energy is zero. This is an astonishing claim, and the immediate objection is obvious. What do we mean by nothing? Tryon's vacuum is not nothing, it is a quantum field governed by the laws of quantum mechanics, existing within a framework of spacetime. Even Vilenkin's nothing is not purely nothing. It presupposes the laws of quantum mechanics and the mathematical structures that make tunneling possible. Where did those laws come from? Why do the laws of physics exist at all? Why is there something rather than nothing? The physicist Lawrence Krauss popularized this idea in his 2012 book, A Universe from Nothing, arguing that the laws of quantum mechanics make it not only possible but inevitable that universes emerge from nothing. The vacuum, he argued, is unstable. It naturally gives birth to universes. The question is not why the universe exists, but how it could fail to exist. But this argument was met with sharp criticism from philosophers, notably David Albert, who pointed out that Krauss's nothing is not nothing at all. Quantum fields, physical laws, mathematical structures, the space of possible quantum states, these are all something. They are a rich, structured, pre-existing framework. Calling them nothing is a sleight of hand. The real question why there is any framework at all, why there are laws, why there is a quantum vacuum with the capacity to fluctuate remains unanswered. This philosophical impasse has led some thinkers to conclude that the question, why is there something rather than nothing, may be beyond the reach of science entirely. Science works by identifying patterns and regularities in the physical world and expressing them as laws, but laws operate within a framework. They presuppose the existence of the things they govern. Asking why the framework exists is asking a question that sits outside the framework. It may require a different kind of inquiry, entirely metaphysics, philosophy, or something we have not yet invented. And yet, there is something thrilling about the attempt. The fact that physicists have been able to push so far to develop rigorous, mathematical models of how a universe could emerge from nothing, or from a quantum bounce, or from a collision of brains, is extraordinary. A century ago, the origin of the universe was considered a religious question, beyond the scope of science. Today, it is a technical question, at the frontier of physics. We may not have the answer, but we have the tools to ask the question in a precise, quantitative, testable way, and that is progress. This is the question that lies at the bottom of the entire inquiry. It is a question that physics, as currently formulated, cannot answer. Physics describes how the universe works. It describes the relationships between quantities. It describes what happens and when. But it does not explain why there is a universe for physics to describe. It does not explain why there are laws, or why the laws are the way they are. These are questions that sit at the boundary between physics and philosophy, between science and metaphysics, and no amount of mathematical ingenuity has yet bridged that gap. Let us step back and consider what we have: 5 major attempts to understand the origin of the universe. The Hartle-Hawking no-boundary proposal. The universe has no beginning, just a smooth bottom. Eternal inflation. Our Big Bang is one bubble in an infinite foam. The cyclic model. The Big Bang is one collision in an endless series of brain collisions. Loop quantum cosmology. The Big Bang was a bounce from a previous collapsing universe. Creation from nothing. The universe tunneled into existence from absolute nothingness. Each is elegant, each is mathematically sophisticated, each addresses real problems with the standard Big Bang model, and each has fundamental limitations. None has been confirmed by observation. None has been universally accepted. None fully answers the question of why the universe exists at all. There is a pattern here that is worth noticing. Each theory pushes the question of origins back one step. Inflation explains the hot Big Bang, but does not explain what caused inflation. Eternal inflation explains inflation, but does not explain why the inflaton field exists. The cyclic model eliminates the need for a beginning, but does not explain why the brains exist, or why they are attracted to each other. Loop quantum cosmology replaces the singularity with a bounce, but does not explain why the preceding universe was contracting. Creation from nothing eliminates the need for a prior state, but does not explain why the laws of quantum mechanics exist. At every level, the why question resurfaces. We answer one question and immediately face another, deeper one. It is as though the mystery is not a particular problem to be solved, but a feature of reality itself, an infinite regression of questions, each one further from the reach of empirical science. This has led some physicists to a provocative conclusion. Perhaps the question of why the universe exists has no answer, not because we have not found the answer yet, but because the question is malformed. Perhaps why is a category that applies to events within the universe but not to the universe itself. Perhaps the universe simply is, without reason, without cause, without explanation. This is not a comforting thought, but it may be a true one, and in science, truth outweighs comfort. Others have taken the opposite view. They argue that the question must have an answer, that the universe cannot be a brute fact, that there must be some deeper level of explanation, mathematical, logical, or structural, that accounts for the existence of everything. Max Tegmark, a cosmologist at MIT, has proposed what he calls the mathematical universe hypothesis, the idea that the universe is not just described by mathematics but is mathematics. Every mathematical structure that is logically consistent exists as a physical reality. Our universe is one such structure among infinitely many. In this view, the question of why the universe exists reduces to the question of why mathematics exists. And mathematics, Tegmark argues, exists necessarily. It could not fail to exist, because its truths are eternal, independent of physical reality. 2 + 2 = 4 regardless of whether anyone is around to observe it. Mathematical structures are not created. They simply are. This is a breathtaking idea, and it is deeply controversial. It is also, at present, untestable. But it illustrates how far the question of cosmic origins pushes us beyond physics, beyond empirical science, into the realm of pure metaphysics and the philosophy of mathematics. We are left with a strange and humbling situation. We can describe the history of the universe with extraordinary precision from 1 second after the Big Bang onward. We can extend that description, tentatively, back to the inflationary epoch, perhaps 10 to the negative 36 seconds. But the true beginning, the first Planck time, the first 10 to the negative 44 seconds remains terra incognita. It is the most important moment in the history of everything, and it is the one moment we cannot describe. The mathematics is striking. We have mapped the cosmic microwave background to a precision of millionths of a degree. We have measured the expansion rate of the universe to within about 1%. We have determined the age of the cosmos to within about 40 million years. We can describe the behavior of particles at energies trillions of times higher than anything achievable in a laboratory. And yet the first instant the true origin eludes us entirely. This is the frontier. This is where we stand, on the edge of the known, staring into a gap that our best theories cannot cross. Now we come to the part of the story that is most difficult to accept, not because it involves complicated mathematics or obscure physics, but because it challenges something we feel deeply in our bones. Something about cause and effect, about beginnings and endings, about the way reality ought to work. We are used to thinking in terms of causes. Every event has a cause. The ball moves because it was kicked. The star shines because hydrogen fuses in its core. The pot boils because heat is applied. Cause precedes effect. Effect follows cause. This is not just a scientific principle. It is the way our brains organize experience. It is the foundation of every story we tell. First this, then that. Because of this, that. But the Big Bang breaks causality in the deepest possible way. If the Big Bang was the beginning of time itself, not an event that happened within time, but the event that created time, then asking what caused the Big Bang is asking what happened before time. And before time has no meaning. It is a grammatically correct phrase that points to nothing. There is no before without time. There is no cause without a sequence of moments in which cause can precede effect. The very framework we use to ask the question dissolves when we apply it to the answer. Let that sink in. This is not a failure of human language. It is not a failure of imagination. It is a feature of the physics. General relativity tells us that time is not a background against which events play out. Time is part of the universe. It is woven into the fabric of spacetime. It began with the Big Bang, just as space did. To ask what came before the Big Bang is like asking what is south of the South Pole. The question feels meaningful. It sounds meaningful, but it has no answer, because it is constructed on a false assumption, the assumption that before is a concept that applies to the beginning of time. Stephen Hawking spent much of his career trying to communicate this point. In his 1988 book, A Brief History of Time, he used the South Pole analogy explicitly. Time, he argued, is finite but has no boundary. It simply ends, or rather, it simply begins in the same way that lines of longitude converge at a pole. There is nothing beyond it. Not empty space, not a void, not another universe, nothing. And nothing here does not mean empty space. It means the absence of existence itself. This is not science fiction. This is the logical consequence of our best tested physical theory. But some physicists are not satisfied with this answer, and their dissatisfaction has led to some of the most profound and disturbing ideas in modern science. Consider the anthropic argument. The laws of physics, as we observe them, appear to be extraordinarily finely tuned for the existence of complex structures like stars, planets, chemistry, and life. If the strong nuclear force were slightly stronger, stars would burn through their fuel in moments. If it were slightly weaker, hydrogen would not fuse at all. If the electromagnetic force was slightly different, atoms would not be stable. If the mass of the electron was slightly different, chemistry as we know it would be impossible. If the cosmological constant, the energy density of empty space, which drives the accelerating expansion of the universe, were much larger, the universe would have expanded too quickly for galaxies to form. If it were much larger in the negative direction, the universe would have collapsed. The degree of fine-tuning required for a universe capable of producing complex structures and observers is staggering. The cosmological constant, in particular, must be tuned to about 120 decimal places, a number so precise that comparison fails. There is no known physical mechanism that explains this. There is no equation that predicts the value of the cosmological constant from first principles. It appears to be, as far as anyone can tell, an arbitrary parameter of our universe, set to a value that just happens to allow complexity in life. Why? This is perhaps the deepest why in all of science. One answer is the multiverse. If there are a vast, perhaps infinite number of universes, each with different physical constants, then it is no surprise that we find ourselves in one where the constants allow life. We could not find ourselves in a universe where life is impossible, because we would not be there to observe it. This is called the anthropic principle, and it is either a profound explanation or a profound evasion, depending on whom you ask. It explains the fine-tuning by dissolving the question. The constants are not tuned, they are randomly distributed across universes. We simply happen to be in a lucky one. Let that sink in. In this picture, there is nothing special about our universe. It is not designed. It is not chosen. It is one of countless bubbles in a cosmic foam, and the only reason we are here to wonder about it is that the constants in this particular bubble happen to allow the existence of wandering beings. Our existence is not the result of purpose. It is the result of probability, filtered by the requirement that observers can only exist in observer-friendly universes. Many physicists find this deeply unsatisfying. It feels like giving up. If the answer to why are the constants what they are is because in other universes they are different, and those universes have no observers, then the question has been shifted rather than answered. We have traded one mystery why the constants are fine-tuned for another why the multiverse exists, and the multiverse, by definition, cannot be directly observed. It is inferred, not detected. It is predicted by theories, but those predictions cannot be tested. This has led some physicists, notably including Steinhardt and Peter Woit, to question whether the multiverse is a scientific hypothesis at all. And yet the alternative is equally troubling. If there is only one universe ours, then the fine-tuning of the constants demands explanation. Why is the cosmological constant so small? Why is the strong force so precisely calibrated? Why are the masses of fundamental particles what they are? If these values are not environmental, if they are the same everywhere, in every possible universe, then there must be some deeper principle that determines them. Some physicists hope that a final theory of everything, a theory of quantum gravity, perhaps will predict the values of all physical constants from first principles, that the constants will turn out to be mathematically necessary, not contingent, that there is only one consistent set of laws, and ours happens to be it, but this hope has no supporting evidence. No candidate theory of quantum gravity has predicted any physical constant from first principles. And the landscape of string theory, which was once hoped to be unique, turns out to allow an astronomical number of solutions. The mystery of fine-tuning is sometimes compared to finding a radio dial set to exactly the right frequency amid trillions of possible settings. One explanation is that someone tuned it deliberately. Another is that there are trillions of radios, each set to a random frequency, and you happen to be listening to the one that works. A third is that there is a mechanism still undiscovered that forces the dial to the correct setting. All three explanations are, in their own way, extraordinary, and none has been established. Others, including Leonard Susskind and Raphael Bousso, have argued that the multiverse is not only scientific but inevitable and necessary consequence of combining string theory with eternal inflation. In string theory, the laws of physics depend on the shape and size of extra dimensions. The number of possible shapes is estimated to be at least 10 to the 500th power, a number called the landscape. Each shape corresponds to a different set of physical constants, a different version of physics, a different kind of universe. Eternal inflation provides the mechanism to populate this landscape, creating pocket universes with every possible combination of constants. Our universe is one point in this landscape, not special, not unique, just one, among an unfathomably large collection. This is, in some ways, the most disturbing conclusion of modern cosmology. Not that we are small, we have known that since Copernicus. Not that we are temporary, we have known that since Darwin. But that we might be arbitrary, that the fundamental laws of nature in our universe are not fundamental at all, but accidental. That physics, the bedrock of our understanding, might be an environmental variable, different in different places, with no deeper explanation. Now consider the arrow of time. The laws of physics, at the fundamental level, are almost entirely symmetric in time. The equations of motion work equally well backward and forward. A film of billiard balls colliding, played in reverse, does not violate any known law of physics, and yet the universe has a clear direction. Time moves forward, eggs break but do not unbreak. Ice melts, but does not spontaneously freeze in a warm room. Stars are born, burn, and die. The universe expands and cools. There is an arrow of time, and it points from order to disorder, from low entropy to high entropy. We experience this arrow so directly, so constantly, that it is easy to forget how strange it is. The fundamental laws do not prefer a direction. Maxwell's equations of electromagnetism are time-symmetric. The Schrödinger equation of quantum mechanics is time-symmetric. Einstein's equations of general relativity are time-symmetric. And yet, the universe is profoundly asymmetric in time. The past is different from the future. We can remember what happened yesterday, but not what will happen tomorrow. A cup of coffee cools to room temperature, but a cup of room temperature coffee never spontaneously heats up. This asymmetry is not a consequence of the laws of physics. It is a consequence of the initial conditions. The laws permit both directions equally. The universe chose one. Why? What selected the direction? What determined the initial conditions? This is where the mystery deepens beyond the reach of any existing theory. The second law of thermodynamics states that the total entropy, the total disorder of a closed system, never decreases. It always increases, or at best, remains the same. This is not a minor principle. It governs everything from the burning of a candle to the heat death of the universe, and it creates a profound puzzle about the beginning. If entropy always increases, then the universe must have started in a state of extraordinarily low entropy. The early universe, despite being hot and dense and seemingly chaotic, was in a state of remarkable order. The gravitational field was smooth and uniform. Matter was distributed evenly. There were no black holes, no galaxies, no clumps. This uniformity, this smoothness, is a state of incredibly low gravitational entropy. It is, in a deep sense, the most ordered state the universe could have been in. And everything that has happened since the formation of stars, the collapse of gas clouds, the growth of black holes has been a process of increasing entropy, of moving from order to disorder. But why did the universe start in such a low entropy state? This is sometimes called the past hypothesis, and it is one of the deepest unsolved problems in physics. The Big Bang did not just produce matter and energy. It produced matter and energy in an extraordinarily special arrangement, one that allowed the arrow of time to exist, that allowed stars to shine, that allowed complexity to emerge. The initial conditions of the universe were not generic, they were astonishingly specific. And no theory, not inflation, not the no-boundary proposal, not the cyclic model, not creation from nothing, has fully explained why. The physicist Roger Penrose has been particularly vocal about this issue. He has calculated that the probability of the universe starting in a state as low entropy as the one we observe is approximately 1 in 10 to the power of 10 to the power of 123. That is not a typo. It is 10 to the power of 10 to the power of 123. A number so staggeringly, incomprehensibly large that writing it out in ordinary notation even with one digit on every atom in the observable universe would be impossible. There are not enough atoms. There is not enough space. There is not enough anything. Penrose argues that this number makes the initial conditions of the universe the most special, the most finely tuned, the most improbable arrangement that physics has ever encountered. And he argues that inflation does not explain it, that inflation, in fact, makes the problem worse, because the inflationary state itself is even more special, requiring even more precise initial conditions. Penrose has proposed his own solution to this problem, called conformal cyclic cosmology, or CCC. In this model, the universe undergoes an infinite sequence of eons. Each eon begins with a Big Bang and ends with an exponentially expanding, empty universe in which all matter has decayed and all particles have lost their mass. At the end of each eon, the universe becomes conformally equivalent to the beginning of the next eon, meaning that, mathematically, the infinite future of one eon can be smoothly joined to the Big Bang of the next. The entropy problem is resolved because the entropy is effectively reset at the boundary between eons, through the loss of all massive particles and the evaporation of all black holes. Penrose has claimed that the CCC model predicts specific patterns in the CMB concentric circles of low variance and has argued that such patterns have been observed. However, his claims remain controversial, and most cosmologists are not yet convinced. What is undeniable is this: the arrow of time, the fact that the past is different from the future, the fact that we remember yesterday but not tomorrow, the fact that things break but do not unbreak. All of this depends on the extraordinarily special initial conditions of the universe. If the Big Bang had produced a universe in thermodynamic equilibrium, the most probable state, there would be no arrow of time, no stars, no planets, no life, no past, no future. Just a uniform, featureless haze of particles at maximum entropy, unchanging for eternity. The fact that we exist, the fact that anything happens at all, is a consequence of the improbable starting point. The universe began in a state of extraordinary order, and it has been winding down ever since. To put this in perspective, consider a simple analogy. Imagine a box filled with gas molecules. If all the molecules happen to be in one corner of the box, a state of very low entropy, they will rapidly spread out, filling the box uniformly. This spreading is irreversible in practice, not because the laws of physics forbid the molecules from spontaneously returning to the corner, but because the number of possible arrangements in which the molecules are spread out vastly exceeds the number of arrangements in which they are clustered. The universe is like that box. The Big Bang was the moment when all the gas was in one corner. Everything that has happened since, every star, every galaxy, every chemical reaction, every thought, is the gas spreading out. We are riding the wave of increasing entropy, powered by the improbable order of the beginning. And here is the deepest puzzle. We do not know why the gas was in the corner. We do not know why the initial conditions were so special. Inflation smooths out wrinkles in spacetime and produces a universe that looks flat and uniform, but it does not explain why the inflaton field itself was in a state of low entropy. It does not explain why the initial state was special. It simply pushes the question back one step, from why was the Big Bang special to why was the state before inflation special. The mystery of the initial conditions is, in some sense, the last great mystery of cosmology. It is the question that sits beneath all other questions, the foundation beneath all other foundations. The physicist Sean Carroll has written extensively about this problem. He has argued that any complete theory of the universe's origin must explain, the arrow of time must explain, why entropy was low at the beginning. A theory that simply postulates low entropy initial conditions without explaining them is incomplete. It is like a theory of gravity that says things fall without explaining why. Carroll has proposed that the arrow of time might be explained by a model in which the universe is part of a larger multiverse, in which entropy increases in both temporal directions from a central, low-entropy event. In this picture, our Big Bang is not the absolute beginning but a fluctuation in a larger structure, and observers on either side of the fluctuation would both perceive time flowing away from the center, both experiencing an arrow of time pointing toward higher entropy. This is speculative, but it illustrates the kind of deep, structural thinking that the problem demands. These are uncomfortable facts. They do not fit neatly into any existing framework. They suggest that something deep about the beginning remains unexplained, something about the initial conditions, the arrow of time, and the nature of entropy that our current theories have not addressed. And behind all of these puzzles lies the deepest question of all. Not how the universe began, but why it began. Not what the laws of physics are, but why there are laws at all. Not what the initial conditions were, but why there were initial conditions, why there was anything to have conditions. The philosopher Gottfried Wilhelm Leibniz asked this question in 1697. Why? Is there something rather than nothing? It is a question that physics has never answered, and perhaps never can. Physics describes the relationships between things that exist. It does not explain why things exist in the first place. It describes the universe from the inside. It does not explain the universe from the outside, because there is no outside. Some philosophers have argued that the question is itself confused. They point out that nothing is not a state that needs to be explained. It is the absence of any state. If nothing were the default, there would be no one to observe it, no framework within which to ask the question. The fact that we are here to ask, why is there something, means that there is something. The question answers itself in a sense. But this argument, while logically clever, does not feel satisfying. It explains why we observe something rather than nothing, but it does not explain why there is something to observe. Others have argued that the universe exists because existence is necessary, that a completely empty reality, with no laws, no space, no time, and no possibility, is logically incoherent. That something must exist because the alternative is not merely unlikely but impossible. This is a view with a long history in philosophy, stretching back through Spinoza and Parmenides. But it is deeply speculative, and it has not been formulated in a way that makes contact with physics. We are temporary structures, patterns of matter and energy that briefly coalesce, think, wonder, and dissolve. And the deepest question we have ever asked, why does the universe exist, may outlast us. It may outlast our species. It may outlast the stars. But the asking of it, here, now, by beings made of stardust on a small blue planet, is itself a kind of answer. Not to the question, but to the question of whether the question matters. It matters. It matters because we are here to ask it, and we are here because the universe began. Where does this leave us? Not just as scientists, not just as thinkers, but as human beings. As creatures who wake each morning on a small rocky planet orbiting an ordinary star in an ordinary galaxy, carrying in our bodies atoms forged in the hearts of stars that died before our sun was born. The story of the universe's origin is not just a story about physics. It is a story about us, about our place, about our significance, or lack of it, about what it means to exist in a cosmos that may have no purpose, no designer, no plan, and yet somehow produced beings capable of asking whether it has a purpose, a designer, or a plan. Consider the sheer improbability of your existence. Forget the fine-tuning of the cosmological constant. Forget the low entropy initial conditions. Focus on something simpler. You are made of atoms. Those atoms were forged in stars. The carbon in your bones was made in the core of a star that lived and died billions of years before our sun formed. The iron in your blood was made in a supernova, a stellar explosion so violent that it briefly outshines an entire galaxy. The calcium in your teeth, the oxygen in your lungs, the nitrogen in your DNA, all of it was cooked inside stars and scattered across space in their death throes. You are, quite literally, made of stardust. This is not poetry. It is chemistry. It is nuclear physics. It is measured and quantified and known. It took the universe approximately 9 billion years to produce the sun and the earth. 9 billion years of star formation, stellar death, chemical enrichment, gravitational collapse, and planetary accretion. Then it took another 4.5 billion years for the blind process of evolution to produce a species capable of asking how the universe began. 13.5 billion years, from the Big Bang to you reading these words. That is the length of the chain that connects you to the beginning. Every link in that chain was necessary. If the initial conditions had been slightly different, if the laws of physics had been slightly different, if any one of a trillion contingent events had gone differently, you would not be here. No one would. This realization has the power to produce two very different emotional responses. The first is terror. The universe is vast, cold, and indifferent. It did not produce us on purpose. We are accidents of physics and chemistry, arising on the surface of a mote of dust suspended in a sunbeam, as Carl Sagan once described our planet. Our lives are brief. Our species is young. The universe was here for over 13 billion years before we arrived, and it will continue for trillions of years after we are gone. In the grand sweep of cosmic time, human civilization is a fleeting spark, a footnote, a ripple in the afterglow of creation, gone before the next chapter of cosmic history even begins. The second response is wonder. We are the universe looking at itself. We are matter that has organized itself into patterns complex enough to be aware. We are atoms that have learned to think, to feel, to love, to mourn, to build telescopes and point them at the sky and ask, where did we come from? In a universe that is overwhelmingly dark, cold, empty and dead, we are a pocket of warmth and light and meaning, not given meaning, self-created meaning, meaning that we build out of nothing, just as the universe itself may have been built out of nothing. There is something profoundly beautiful about this. The same laws of physics that govern the explosion of a supernova govern the firing of neurons in your brain as you listen to this. The same quantum mechanics that describes the fluctuations from which galaxies grew describes the chemistry that makes your cells function. There is no separate category for living things. There is no special ingredient that separates us from the rest of the cosmos. We are made of the same stuff. We follow the same rules. We are continuous with the universe, not separate from it. And our ability to understand the universe, to reconstruct its history, to predict its future, to grasp, however dimly, the nature of its beginning is itself a product of the universe's own evolution. The physicist Freeman Dyson once wrote that the universe in some sense knew we were coming, not in a mystical or teleological sense, not because there is a plan, but because the laws of physics, as they are, allow for the emergence of complexity, and complexity, given enough time and enough space, produces observers. We are what the universe does when it has 13.8 billion years and the right set of initial conditions. We are not separate from the story. We are the story, becoming aware of itself. But we should be careful not to take too much comfort in this. Our understanding is incomplete, deeply, fundamentally incomplete. We do not know what dark matter is. We do not know what dark energy is. Together, they make up 95% of the universe, and we cannot explain either of them. We do not have a theory of quantum gravity. We do not know what caused the Big Bang. We do not know whether the universe is finite or infinite, whether it is the only universe or one of many, whether time had a beginning or stretches back forever. We have mapped the visible surface of an ocean whose depths remain entirely unexplored. And perhaps this is the most important lesson. The universe does not owe us answers. It is under no obligation to be comprehensible. The fact that we have understood as much as we have, that we have reconstructed the history of the cosmos from the first fraction of a second to the present day, using nothing but light and mathematics, is itself extraordinary. It is a testament to the power of human reason, but it is also a reminder of the limits of human reason. There may be truths about the universe that we are not equipped to grasp, not because they are hidden, but because our minds, shaped by evolution for survival on the African savanna, are simply not designed to process them. We sit on our small planet, beneath a canopy of stars, and we ask the oldest question, how did all of this begin? And the answer we have found is this: we do not fully know. But we know more than anyone who came before us. We know that the universe is expanding. We know that it is cooling. We know that it was once unimaginably hot and dense. We know that the seeds of all cosmic structure were quantum fluctuations, amplified by inflation, frozen in the CMB, and nurtured by gravity into the galaxies we see today. We know that the atoms in our bodies were forged in stars. We know that the story of the cosmos is the story of matter organizing itself into ever greater complexity, from quarks to protons, from protons to atoms, from atoms to molecules, from molecules to cells, from cells to brains, from brains to the question itself. There is a peculiar loneliness in this knowledge. Every other question human beings have asked about the weather, about disease, about the movements of planets, has eventually yielded to investigation. We learned the causes of eclipses. We learned the structure of atoms. We learned the age of rocks and the shape of continents and the mechanism of heredity. But the question of the ultimate beginning may be different. It may be the one question where the answer is permanently inaccessible, not because we are not clever enough, but because the information has been erased. The expansion of the universe has stretched the evidence beyond recovery. The first Planck time is hidden not just by our ignorance, but by the physics itself. It is as if the universe has burned the first page of its own autobiography. And perhaps that is fitting. Perhaps the universe is not obligated to remember its own origin. Perhaps the first instant, like the private moment of a birth, is something that happens in darkness, unseen and unrecorded. What matters is not the first instant, but the story that followed. The long, slow, patient unfolding of complexity, the galaxies, the stars, the planets, the oceans, the first cell, the first thought, the first question. We are temporary structures, carbon-based patterns, organized by billions of years of evolution, sustained for a few decades by chemical reactions, and then dissolved back into the raw material of the cosmos. Our atoms will be recycled into new stars, new planets, new structures. Nothing of what we are will be lost to the universe. But everything of what we know, what we feel, what we wonder that will be gone, unless we pass it on, unless we write it down, unless we tell the story. And we know that the story is not over. It is still being written, in every observation made by every telescope, in every equation scrawled on every whiteboard, in every moment of curiosity felt by every mind that looks up at the night sky and wonders. We began this journey with a question, the oldest question. How did the universe begin? We have traveled from the vast reaches of the observable cosmos 93 billion light-years across, 2 trillion galaxies, 700 sextillion stars backward through time, past the formation of galaxies, past the ignition of the first stars, past the dark ages, past the release of the cosmic microwave background, 380,000 years after the beginning, past nucleosynthesis in the first 3 minutes, past the quark-gluon plasma in the first microsecond, past the electroweak transition, past the grand unification epoch, past the inflationary expansion, back, further and further, to the first Planck time, 5.4 times 10 to the negative 44 seconds, where our physics fails and our understanding ends. We have seen how Edwin Hubble discovered the expansion of the universe, how Arno Penzias and Robert Wilson accidentally detected the afterglow of creation, how satellites like COBE, WMAP, and Planck mapped that afterglow with extraordinary precision, revealing the seeds from which all cosmic structure grew. We have explored the puzzles that the standard Big Bang model could not solve: the horizon problem, the flatness problem, the monopole problem, and the bold theory of cosmic inflation that Alan Guth proposed to resolve them. We have examined the deepest attempts to understand the true beginning, the Hartle-Hawking no-boundary proposal, which eliminates the singularity by rounding off the bottom of time, eternal inflation, which embeds our Big Bang within an infinite, ever-expanding multiverse, the cyclic model, which replaces the beginning with an endless series of collisions between higher-dimensional brains, loop quantum cosmology, which replaces the singularity with a bounce, and the idea that the universe tunneled into existence from absolute nothingness. Each theory is brilliant, each is incomplete, and together they paint a picture of a beginning that is far stranger, far more mysterious, and far more humbling than any creation story ever imagined by any human culture. The universe may not have a cause, it may not have a before, it may be one of infinitely many. It may have bounced from a previous cosmos, it may have emerged from nothing, through the strange logic of quantum mechanics. We do not know. And the honesty of admitting this, the courage of standing at the boundary of knowledge and saying, "We do not know, but we are looking," is perhaps the noblest expression of the scientific spirit. What we do know is this: you are here, right now, on a planet orbiting a star, in a galaxy among trillions, in a universe that is 13.8 billion years old. Every atom in your body has been on a journey of unimaginable length and complexity. The hydrogen atoms in the water in your cells were forged in the first 3 minutes after the Big Bang. They are almost as old as the universe itself. They have been part of interstellar gas clouds, part of stars, part of supernovae, part of the solar nebula from which our Sun and Earth condensed. They have travelled billions of light years through space and billions of years through time to be here, now, in you. You are the universe's autobiography, written in atoms. And the question of how it all began, the question we have spent these hours exploring, is not just a scientific question. It is a mirror. When we ask how the universe began, we are asking where we come from. When we probe the first fraction of a second, we are probing the deepest foundations of our own existence. When we stare at the blank wall and admit that we cannot see beyond it, we are confronting the limits not just of our instruments, but of our understanding, our language, and perhaps our minds. Somewhere right now, in a laboratory or an observatory or a quiet office, a physicist is working on this problem. They are filling a whiteboard with equations, or running a computer simulation, or analyzing data from a telescope pointed at the edge of the visible universe. They are chasing the same question that the first humans asked when they first noticed the stars. They are doing it with better tools, better theories, better data. But they are asking the same thing. How did it start? Why is there something? What happened in the first instant? The answer may come tomorrow, it may come in a century, it may never come. But the asking is what makes us human. The willingness to confront the unknown, to sit with uncertainty, to follow the evidence wherever it leads, even when it leads to the conclusion that the question is bigger than we are. The universe began. That much we know. It began in fire and fury and light, in temperatures and densities beyond comprehension, in a state so extreme that our best theories dissolve into silence. From that beginning, through expansion and cooling, through the formation of atoms and stars and galaxies and planets and oceans and cells and minds, it arrived at this moment, this precise moment, when a pattern of atoms complex enough to ask questions looks back across 13.8 billion years of cosmic history and whispers, how did it start? The answer is still being sought, but the seeking itself, the act of asking, of measuring, of wondering, is the universe's most extraordinary product, more extraordinary than galaxies, more extraordinary than supernovae, more extraordinary than the cosmic microwave background or the inflationary expansion or the fine-tuning of physical constants. Because the universe has been expanding and cooling for nearly 14 billion years, and for almost all of that time, no one was watching, no one was asking, no one knew, and now someone does. The night sky is full of light from the beginning. It washes over us, unseen, unheard, unfelt. It has been travelling since the universe was young. It carries the imprint of the first atoms, the echoes of the first moments, the signature of the origin of everything. And on one small planet, orbiting one ordinary star, in one ordinary galaxy, among trillions, a species has built instruments sensitive enough to detect it, mathematics powerful enough to decode it, and minds curious enough to spend a lifetime trying to understand what it means. We are the universe's way of knowing itself, and the story of the beginning, however incomplete, however uncertain, however humbling, is the most important story we will ever tell. It is the story of everything, the story of nothing becoming something, the story of silence breaking into sound, of darkness giving way to light, of emptiness filling with form. Consider one final thought. The cosmic microwave background, that ancient whisper from the dawn of creation, is not just out there, in deep space, detectable only by satellites and radio telescopes. It is here. It is passing through this room right now. It is passing through your body right now. Approximately 411 photons from the cosmic microwave background occupy every cubic centimeter of space. You are bathed in the light of the Big Bang at this very moment. The beginning is not a distant event, locked away in the past. It is present. It surrounds you. It permeates every corner of the universe, every instant of every day. Those photons have been traveling for 13.8 billion years. They have crossed billions of light years of expanding space. They have watched galaxies form, stars ignite, supernovae explode, black holes grow, and planets cool. They were released when the universe was just 380,000 years old, and they will continue traveling until the universe ends, if it ends, or forever, if it does not. They are the oldest travelers in existence, and they are here, now, completing their journey through the space you occupy. And though the final chapter has not been written, the fact that someone is writing it, the fact that atoms have arranged themselves into beings that can contemplate their own origin, is perhaps the most profound thing the universe has ever done. That is the story of the beginning. It is incomplete. It will remain incomplete for a long time, perhaps forever. But the incompleteness is not a failure. It is an invitation to keep looking, to keep asking, to keep pushing the boundaries of what we know into the vast, dark, silent, unknown. The universe began, and we are still learning how to listen to its first words. End of script. Total word count, 19,619.